Right, so we have the next question in the series as question number 22 from Oxford. Before you look into this question, I would highly recommend you to get back to my previous videos and kind of watch them through, because this has a lot to do with those questions, right? An aircraft is at flight level 140 with an indicated airspeed of 210 knots and a true outside air temperature of -5 degrees Celsius. The wind component is -35 knots. When the aircraft is at 150 nautical miles from the reporting point, ATC requests the crew to lose 5 minutes by the time they get to the beacon. How much do they need to reduce indicated airspeed? It's a very common practice whenever air traffic control needs to sequence you. One of the techniques that they use is time-based separation. And they can ask you to kind of be early by a certain amount of time or be late, or to keep up your speed and be on time, right? So the question here is, how much speed should you actually reduce so that you can be delayed by a fixed amount of 5 minutes by the time you get to a reporting beacon? All right, so let's look at this question in two different ways. Not two different ways, actually. It's a different approach to the concept, and the technique is exactly the same. So whichever you wish to kind of adopt, you can take it. I'll be going through both together, side by side. And since, as we have discussed earlier, when you have questions to do with time, speed or distance, etc. in the aircraft, it's more talking about the ground speed, because that is the speed which gives you an exact indication of the time estimates. And we have done particular questions on this before, where we find the ground speed to kind of find the time estimates, and I've kind of elaborated on why time estimates are important as well. All right, so without any further delay, let's get into the question. Once again, let's kind of write things down here. Aircraft is at flight level 140. All right, so the aircraft is at 140. I generally have the habit of kind of writing the points down. You might feel that might take some time, but that's fine, because that kind of, as you write it through, you are kind of making it ordered in your brain, and that really helps for your approach as well. So flight level 140, the aircraft is flying with an indicated airspeed of 210 knots, and an outside air temperature of -5 degrees Celsius. The static or the outside air temperature. The wind component is given as -35 knots. Now, when you have a negative wind component, obviously it's a headwind, and the negative kind of shows that your ground speed is going to get reduced. It's kind of opposite to the path of the aircraft, right? -35 knots. When the aircraft is at 150 nautical miles from the reporting point, so let's draw the aircraft 120 nautical miles from the reporting point. So let's keep the reporting point here. This is the reporting point, right? And the aircraft is 120 nautical miles from the 150 nautical miles from the reporting point. And that's when the aircraft, the ATC requests the crew to lose 5 minutes by the time they get to the beacon. So the aircraft is currently here. I'm going to draw the top view of that. So while the aircraft is 150 nautical miles to the destination or to the beacon, the ATC advises the crew to kind of lose some time so that they can be delayed by 5 minutes by the time they get to the beacon. And obviously, to get delayed by 5 minutes, you have to reduce your ground speed, right? Lesser the speed, the more you take to reach there, and hence the delay. All right, so it's looking at the ground speed basically, because time estimates are all connected to ground speed. So what we have is the indicated airspeed and the wind component, and we know that if we can actually find the true airspeed, so obviously from the indicated airspeed, you know how to find out the true airspeed. And if you can find the true airspeed, and if you can apply this particular wind component to it, what can you find out is the ground speed. Now, what are we trying to do here is we're trying to find out what would be the time, or how long would it take for the aircraft to reach to the beacon if it had flown with the normal ground speed. And then we kind of add 5 minutes to it, because we are supposed to take 5 minutes longer, and then we reverse it all the way and find the ground speed, and then we find the TAS using the same wind component, and then we find out the indicator airspeed which is asked in the question, and then we find out how much to reduce. That's one way of doing it. Okay, so let's do that. So let's find out the true airspeed. Now to find out true airspeed, we have the outside air temperature given, we have the indicator airspeed, flight level. That's it. You can grab your CX3 and let's find out what the true airspeed would be. So as we have done previously, we are kind of dwelling around airspeed. So you have to go to the airspeed tab, and outside air temperature, make a note that it is in degrees Celsius, and you can enter 5 with a minus there, and then we can go all the way down to calibrated airspeed. Now remember, in modern, calibrated airspeed is indicator airspeed corrected for instrument and pressure or position errors. In modern aircrafts, these errors are kind of made to the minimum, and if nothing much is specified in the question, you can take indicator airspeed as calibrated airspeed. Let me kind of jot that down here. So we are taking indicator airspeed as calibrated airspeed. You can keep this in mind because it could be helpful. Now calibrated airspeed is indicator airspeed, which is 210 knots, and you have a pressure altitude of, it's a flight level of 140, and that gives you a pressure altitude of 14,000 feet. Right, that's it. You'll get the true airspeed straight away. True airspeed is equal to 262 knots. All right, yeah. So with 262 knots of true airspeed, let's kind of apply the wind component here. The wind component is minus 35 knots. That is 35 knots of headwind that goes from the true airspeed. So it is 262 minus 35, and your ground speed is 227 knots. Right, now once you have the ground speed, we have the distance, which is 150 nautical miles. You can find the time, and that time is the estimated time interval from the current location of the aircraft to the beacon with the ground speed of 227 knots. So with this ground speed, and we have the distance as 150 nautical miles to the beacon, we can find out the estimated time interval to beacon, and that's going to be distance, which is 150 nautical miles, divided by speed, which is 227 knots. And for obviously you're going to get the answer in minutes, and that is 39.64. So as I have told you before, I don't kind of round off instantly. I just carry at least 2 to 3 digits and go all the way down to the final value and look at the options and kind of round off sensibly. Okay, you can look at the options here. It's kind of 15 knots, 25, 30, 20. It's not that far apart and not close as well. So let's keep the decimal places intact, and therefore 39.64 minutes. Perfect. Now you are asked to kind of establish a delay of 5 minutes, and that 5 minutes gets added to this time. Remember, when there is a delay of 5 minutes, do not subtract it. That's also a kind of practice that I've noticed, because it's instant thought that you're delaying something, which means you're kind of taking something off. No, you're delaying a time, which means you're adding more time. You're getting late, right? Therefore, this 5 minutes is kind of added. So here we have a delay here, a deliberate delay of 5 minutes, and that gets added to the time here. So it is 39.64 minutes plus 5 minutes. That is 44.64 minutes. Now, the distance being the same, 150 nautical miles with 44.64 ETI, the new ETI, let's find out the ground speed. So we have the time here and we have the distance, which is again the same. So we know speed is equal to distance divided by time, and therefore the ground speed is equal to distance of 150 nautical miles divided by the time of 44.64. Remember, this is in minutes, which means you have to convert it to hour by dividing by 60. Now these are the very, very small yet important points which you have to remember, because you might know the concepts, you might know the pathway, but you might go in all these things. Very, very small but important points to note. So let's find out 150 into 60 divided by 44.64, and that's going to give you 201.61 knots. And for obvious reasons, we are expecting a ground speed that is lesser than 227 because only that can amount a delay of 5 minutes. Now we are almost close to the answer. If a ground speed of 201.61 knots, as I told you, we are kind of reverse assessing now the whole question. The wind component is assumed to remain the same, which is minus 35 knots of headwind. So let's bring that into picture now. So we have wind component of 35 knots. Now, one thing which you have to be very careful here is you apply the wind component to the task and you get the ground speed, which means taking the headwind component here, task plus the headwind component, that is going to give you the ground speed. And the headwind component is minus 35 here. That is the reason why I took it as plus. You can also consider the same equation as task minus headwind. In that case, be careful that you just have to take the headwind component, the magnitude itself, and not the sign, which means task minus headwind is the ground speed. You have to find out the task here, which means task is equal to ground speed plus headwind. We are taking only the magnitude of the headwind, and the ground speed is given as, we got it as 201.61 plus 35 knots of headwind, and that is going to give you the reduced task, which is 236.61 knots. So it's kind of reverse as in the whole situation. Now with this, a task of 236.61 knots, now we can kind of approach this question in two different ways. Let's see that. So method number one is the normal method. We're just kind of going exactly the way we came in, all the way on the reverse direction, where we have a task of 236.61 knots. We have outside air temperature of minus 5 degrees Celsius, and we have pressure altitude of 14,000 feet. Using your CX3 airspeed tab, you can find out the indicator airspeed. What you'll be getting is a calibrator airspeed. As I've told you, you can take it as indicator airspeed. Let's go all the way back, and the task is now 236.61, and outside air temperature is minus 5 degrees Celsius. CAS is something we should find out, and pressure altitude is 14,000 feet, and that's going to give you a calibrated airspeed, which is the indicator airspeed of 189.3 knots. Right now, there is a different way by which you can actually find out the indicated airspeed. Right, so let's see that. The indicated airspeed, so in technical general, we have seen that indicated airspeed is kind of, it represents the dynamic pressure, or you can see dynamic pressure is an indicative of indicator airspeed, because that's what causes the capsule of the ASI to expand, which in turn comes up as a reading on the dial, which we call as airspeed indicator, sorry, airspeed, right? And dynamic pressure, as we know, is the product of the density rho and square of the velocity, and we very well know that this velocity we're looking at in the equation is nothing but the true airspeed. So you can kind of see that the indicated airspeed is proportional to the true airspeed. Right, remember, indicated airspeed is not equal to half rho v square. It's an indicative of half rho v square. So it's not that indicated airspeed is proportional to square of task. That doesn't work like that. Dynamic pressure is proportional to square of task. Indicated airspeed is just an indicative of dynamic pressure, and therefore indicated airspeed is proportional directly to task. Right, so having this understanding, we have the indicated airspeed which is given in the question right here, which is 210 knots divided by the new reduced indicator airspeed is something which you have to find out. That's equal to the task which we found out initially, corresponding to 210 knots of indicated airspeed, was right here, which is 262 knots. Right, so let's write that down. 262 knots divided by the indicated airspeed, the true airspeed corresponding to the reduced true airspeed. In fact, that is right here, which is 236.61 knots. Right, now with this understanding, let's find out indicated airspeed by cross multiplication. Therefore, it is 210 into 236.61 divided by 262, and that is 189.6 knots. So you can kind of find indicated airspeed using both the methods, whichever you find it easy, either using CX3 or by using the fraction method and cross multiplying it. Either way it should work. All right, so indicated airspeed is 189 knots or 189.6 knots, and you are asked to find out what is the amount by which you need to reduce indicated airspeed. So the initial indicated airspeed is 210 knots. So the change in indicated airspeed required is 210 knots minus 189. I'm just taking 189 because I can see from the options that rounding off is fine. And that's going to give you 21 knots. So the indicated airspeed has to be decreased by 21 knots, right? Let's look at the options here. 21 knots, the one that is closer to it is 20 knots, and therefore the answer. All right, so you cannot call this as a different approach, but we kind of find out the reduced task, and then from there you can find out indicated airspeed by using CX3 and go exactly in the reverse order, or you can use the cross multiplication technique to find out the indicated airspeed. All right, I hope this question made sense. This is not a very difficult question. Only thing is you kind of have to analyze a bit. And as I've told you, if you haven't watched my previous classes or the recorded videos, do watch them, because we have kind of integrated a lot of information from those videos into this question. All right, so let's move on to the next question.